We're going to be looking at few gas laws here, and one of them, probably the biggest one, is pressure times volume is always constant. And that constant, usually it's equal to capital N times K times T. Now let me give you some information on them, what each one. So the pressure times the volume equals N times K times T. We're going to change that in a minute. You'll see that. K is a constant. That's equal to 1.38 times 10 to the negative 23 joules per Kelvin. Okay, temperature has to be in Kelvin. N, what's N here represent? It's got, and one is molecules, one is moles.
The capital N is molecules, the large.
Molecules, okay. N is the number of molecules. Small n is the number of moles. So here's an example here. Our lung, and I'll tell you a story on, yeah, it's recording. A personal lung might hold, your lung, 6.0 liters of air, which if you convert that, that's approximately, the conversion 1 liter equals 10 to the negative 3 cubic meter. So your lung can hold 6.0 times 10 to the negative 3 cubic meters. At temperature, your lung can hold at what temperature? 310 degree Kelvin. And at atmosphere pressure, at P atmosphere, which is 101 kilopascal, or 1.01 times 10 to the 5th. When you take a deep, deep breath, you see, you can inhale up to 6 liters. Up to. When I had my open heart surgery, they bring me this machine. They say, see if you can get to 4 liters. Like, huh? That's a lot, 4 liters. I go, it's half a liter. So my son comes in, I go, Joseph, can you try this? Because there's no way you can get to 4 liters. He goes, and he goes 4 plus, like, oh, it can be done. So that became my mission. I got to get it to 4 liters now. I'm up and every day practicing every hour, every 15 minutes to get it to 4 liters. But you can go up to 6 liters. That's actually a lot when your lung expands. But that's only at atmosphere pressure at this temperature. You know. Now here's what we know about air surrounding us. The air surrounding us has 21% oxygen. %20 oxygen in air. And the question, can you tell me what the number of molecules of oxygen in your lung? So N is the number of molecules. It looks messy here. That's what N, that's 1 L. It looks like 2 L's. The number of molecules. Find the number of oxygen molecules. First, let's begin C. What N is in terms of air, then we'll take the 21% of that. We know P times V equals capital N times K times T. The pressure is 101 or 1.01 times 10 to the fifth. That's atmosphere pressure. The volume of the lung, which is what? 6.0 times 10 to the negative 3 equals N times K, which is 1.38 times 10 to the negative 23 times the temperature in Kelvin, which is 310. We can get the number of molecules. We're not saying oxygen, just air molecules. This is air. The number of air molecules in your lung, if you just take a deep breath, will be 1.01 e to the fifth times 6.0 e to the negative 3 divided by 1.38 e to the negative 23 divided by the 310. And according to my calculator, if I push all the right button, we should have 1.417 roughly times 10 to the 23 molecules. We're looking for the number of oxygen molecules. Well, since oxygen is 21% of that, what is 0.21 times that number? So multiply that number by 0.21, and according to this, it should be about 3.0 or 2.97, I don't know how many, I carried all the digits here, times 10 to the power 22 oxygen molecules. So that's how many oxygen molecules in your lung if you take a deep breath. Now, earlier today I said how many moles in a molecules, and Mike said Avogadro's number, 6.022 times 10 to the 23, and he is right. 1 mole is equal to 6.022 times 10 to the 23 molecules. So if I want to change the equation in terms of moles instead of molecules, so I go, we said P times V equals what? Capital N, which is the number of molecules, times K, which is a constant, times what? The temperature? Well, let's say I want to use moles. We use small n. Moles is small n, molecules is capital N. So I know if I want to use small n, and so n equals 6.022 times 10 to the 23 times the number of molecules there. Actually, I wrote capital N. Capital N equals the number of molecules, or number of molecules is you take the number of moles and you multiply each one, because each one of them has 6.02 times 10 to the negative 23. Not negative, positive 23, Avogadro's number. 6.022 times 10 to the 23 times the number of moles, if you want to figure out how many molecules there is. So if I replace a capital N with this number, pressure times volume equals, capital N will use what? 6.022 times 10 to the 23 times small n times K times T. We said K is a constant. What was K equal to?
1.38 times 10 to the negative 23.
1.38, you said,
Yep.
times 10 to the negative 23
Yep.
times T. So if I multiply these two numbers, let's take my calculator and multiply these two numbers and see what are we going to have. 6.022 e to the 23 times 1.38 EE to the negative 23, and you end up with 8.3 1 times N times T. So let me define a dummy variable called R, and let's give it the value of 8.31. So I can say now PV equals what? nRT. And that's the equation that a lot of you probably seen, and R equals only 8.31. But that's where it came from. And again, small n, n is the number of moles here. If they ask you for moles, you want to use this one. If they ask you for molecules, you go P times V equals N times, capital N times K times T. K equals 1.38 times 10 to the negative 23, and capital N is molecules. So it depends which equation or what they want to find. They want to find moles or molecules. If they said how many molecules, you can do this, or you can do this one and go, wait a minute, each mole has that many molecules in it, and multiply them out. Or you can do it this way. If you want to see pressure times volume as constant, you want to see that experiment? I used to take a balloon every time I went flying with my kids with me, and I'll blow the balloon and I'll put it on the seat of the plane there. And as the plane goes up, 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 higher and higher, you see the volume expands. Why? Because the pressure is less. That number has to stay the same. So if P times V has to stay constant, it doesn't change. If this number, the pressure drops by 20%, that means the volume has to increase by what? 20% to make for the difference. So when you go up, the pressure actually decreases, the balloon becomes much bigger. And as you start descending, the pressure starts to increase, the volume starts to decrease. But pressure times volume always stays the same. It's a constant value. Here's a question, let's see. How many moles? Moles, not molecules. Moles of air in a basketball. Excuse me, my throat for the last 3 days. In a basketball. That's really the question. We have to give you a few things about the basketball. Let's assume the pressure of the basketball when you fill it with air is 171. Now look, I'm writing kPa. What does the K stands for? 1,000. That's equivalent to 171,000 Pascal. That's the pressure, kPa. Temperature. The temperature is 293 Kelvin, 20 degrees Celsius. And the diameter of the basketball, diameter, not the radius, 30 centimeters. Which means the radius is what? 15 centimeters. And we're looking for N. That's what the question is. Small n, moles. So I'll put it here. Pressure times volume equals nRT. R is a constant. 8.31. I'm looking for N. I know the volume. No, I don't know the volume. I know the pressure, 171,000. I don't know what the volume is. I'll leave it blank. I'm looking for N. I know what R is, 8.31. I know what T is, 293. And it has to be in Kelvin. If you write this in Celsius, it will not work. So notice I'm looking for N. If I know what the volume is, I'm done. Well, the shape we're looking at, it is a sphere. 3-dimension. Looks like this. And the volume of a sphere, if you grab a math book, it'll say 4/3 pi r cubed. Or if you look on Google and research that, what's the volume of a sphere? That's what the volume, 4/3 pi r cubed. So the volume of this shape is 4/3 pi, and r is what? 0.15 cubed. Four divided by 3 times pi times 0.15 cubed. The volume of the basketball, 0.014. So if you put that in, I'm carrying all the digits, times 171,000 divided by 8.31 divided by 293. The number of moles is 0.993 moles. Again, I carried all the digits. If you want to figure out the number of molecules, you go, well, we know the molecule was a 6.022, is it? Times 10 to the 23. Is that what that number is? Avogadro's number? You multiply that by the number of moles, which is what? 0.993. We can tell you how many molecules we got there. So we have 5.98 times 10 to the 23 molecules. Okay. Let's see what happens here to gases. Now, let's say we have a container here. I'll derive the equation. Has a piston, you can push down it to shrink it. And it, like, nothing really leaks. We have all these molecules inside that. What happens if you push down and you shrink that size now? Push down on it. Let's talk about isotherm. Now, if the number of molecules N stayed the same and the temperature T remained the same, so nothing leaked out of that container, we're still in the same room. Let's look, we'll call this case 1 and this is case 2. We know pressure 1 times volume 1 equals nRT. And pressure 2, volume 2 equals nRT. R is a constant. If n doesn't change and neither t changes, that tells me this number has to equal to this. Because there's no change in n and no change in t. And R is what? It's a constant, 8.31. So that tells me P1 times V1 equals what? P2 times V2. Which means pressure really varies inversely with volume. Varies inversely. What does that mean? If one decreases, the other one increases. But this is the equation I'll be interested in. Pressure 1 times volume 1 equals pressure 2 times volume 2. If the number of molecules and the temperature remain the same. Missing an E from this. Oh, that's an E, I guess. That's a dot there. If N and T remain the same, then P1 V1 equals P2 V2. So we can look at a jar like this where we decrease the volume, we can calculate what the pressure inside that one might be. So let's look at this example. Give us some numbers here. Here's what we know. Initially, the pressure applied to the piston is 130 kilopascal. So the pressure here, P equals 130 kPascal. The height of the piston above the base was 25. The height is 25. And that's in centimeters. When additional mass is added, we put more pressure on it. The pressure increased to 170 kilopascal. Assume the temperature and the number of molecules stayed the same. Can you calculate what the height is? That's what the question is. Let's look at this equation. Pressure 1, volume 1 equals pressure 2, volume 2. Pressure 1 is what? 130. What's the volume? A volume of a shape like this is the area times the height. The area times the height, and the height was what? 0.25? Should equal pressure 2, which is 170, times the volume, which is area, times the height, which we don't know. I don't even have to know if that was actually a square container, round one, rectangular shape. Doesn't matter what the shape. As long as the same container, the volume is always the area times the height. Since the area didn't change, these two will cancel each other out. So 130 times 0.25 equals 170 times h. Can I get what the height is? 130 times 0.25 divided by 170 is going to go roughly 19 centimeters. So this equation is if N and T are the same. If the temperature remains the same, we're assuming there's no molecules we're leaving. So if the temperature remains the same, this is for same temperature, this equation. Okay, what happens if the temperature is not the same? What about if you don't have same pressure, constant pressure, assuming the number of molecules again didn't change? So this is for same temperature. This equation becomes P1 V1 equals P2 V2. So what about if we have same or constant pressure? That means the pressure didn't change. So that's same P, and again the number of molecules stayed the same. We're not going to change the number of molecules. That means something else got to change. If the volume changes, that means the temperature has to change. An example, you bring in a container to this room, you put it here, a gas tank, and you turn the air conditioner on. Now the temperature changes. The pressure never changed, still atmosphere pressure. Again, P times V equals nRT, or P equals nRT over V. So if you have two cases with different temperature, again, two containers, the pressure staying the same, if the pressure is the same, P same. So for the first one, P1 equals N1. I'm assuming N is not going to change. Let's leave it N as N. I call it N1. I'm not changing N. The number of molecules are the same. N times R times T1 over V1. And pressure 2 equals N times R times T2 over V2. Well, if the pressure doesn't change, if pressure 1 equals pressure 2, that means these two equations will have to equal to each other. And since NR on both sides, you can cancel that out. The equation becomes temperature 1 over volume 1 equals temperature 2 over volume 2. Again, this is when what? The pressure is the same pressure. So when the pressure is the same, if you adjust the temperature, the volume will adjust. But here backward, because if you shrink the temperature, you lower the temperature, what's going to happen to the volume? You're going to shrink the volume. So if the temperature gets smaller, the volume gets smaller. If the temperature gets bigger or larger, the volume gets bigger. Because you have to keep the ratio the same. If one increases, the other one has to increase. The other one is backward. If one increases, the other one has to decrease. This one, if this one increases, this has to increase to keep the ratio the same. So what happens, you get in your car on a cold day, you go to drive your car to work, you get that warning, check air pressure. Temperature get lower there. Again, the reason the volume of the tire doesn't change, if this one gets smaller, when you divide these, that number gets smaller. Okay. So that's ideal gases.